All right, this is take 2 of part 2 of this exercise solution because, let's see here, can I actually get what the previous solution that I did was? Yes, it was here. So the previous solution here for multiplying two numbers represented as strings was using this procedure, and we saw that it was a bit slow. So we're going to do some things to try to improve it. And one of the main things that we're going to look at is here, because for the result we have the result as an integer here, and the way that we add to the result is by multiplying the digits together, and then adding them to the result, and taking care of like the digits, like the significance of the digits, by multiplying by 10 to some exponent. And it turns out this is really slow. I probably shouldn't cover my mic like that. Okay. It turns out this is slow because we have to raise 10 to a power, and so this can be really large, and then we have to do all these multiplications and stuff. It would be a lot easier because, so all we're doing here by multiplying by 10 to some power is we're making sure that we're altering the proper digit of the result. So if we were storing the digits of the result in a list where each entry corresponded to one of the digits of the result, then we can update the result by updating the proper digits rather than by adding the product of the digits times 10 to some power. And so the main improvement that we're going to make here is we're going to, instead of initializing result as an integer, we're going to initialize result as a list, and the values of the list will represent digits of the result, and the values will be the values that those digits need to take on. Okay, so I'll go back to the problem description. I've already refreshed it. So let's start this code. So the first thing that we're going to do is we're going to take care of the base case. So if num1 is 0 or num2 is 0, then we're just going to return 0. Okay. Okay, then the next thing that we're going to do is, now in the previous solution, I just converted to integer like as soon as we were using each digit. I'm actually going to convert digits to integers, or at least create lists of digits as integers. And this is going to make the code look a little cleaner, but the other thing is that having this as a separate step here will allow me to talk in a little more detail. So digits 1, what we could do is we could just say int n for n in num1. This will convert all of the strings to integers. But there's a better way to do this. Do ord n minus ord 0, the string 0, for n in num1. And what is this? So ord, you plug in a string and it returns a Unicode code point. And I'm not super familiar with all the details, but basically there are integers corresponding to every like single character string. And so all of the numbers from 0 to 9 have integers in this way. And going to our notes here, I'll scroll down. The way that this works is ORD of the string 0 happens to be 48. And ORD of the string 1 is 49. It continues in a linear fashion. Then ORD of 9 is 57. Okay, so what we can do is we can get the proper integers in this fashion by taking ORD of n minus ORD of 0. And you can just like verify that that works because like ORD of n is going to occur n places after ORD of 0. And so the corresponding integer will be n plus ORD of 0, which is 48. And so if you subtract ORD of 0, then you shift everything to start at 0. So yeah, this will give us the proper integers. And this, I guess, is faster. I don't understand all the details of why it's faster, but basically ORD, like you just plug in it's a very simple mapping because you just plug in a single character string and it just gives you a number, well, an integer. But then if the integer function has to do some like string parsing, which I guess is just more computationally intensive. And I guess that makes sense because the int function has to be able to handle like all like strings of various lengths. And so it certainly is a more complicated function, and so I suppose that just makes it faster or makes it slower. I don't know all of the details behind why it works, but in any case, this is a slightly optimized solution. And so then digits 2, we could do the same thing for num2, for n in num2. Okay, so this is how we start. Okay. So then we need to prepare the result list. Okay, so n1 and n2 are going to be the lengths of these lists. And I guess we could have done length of num1 and num2 instead of digits 1 and digits 2. It doesn't really matter. But then the result, okay, so the result is going to be a list. And each digit in the list is going to correspond to a digit in the resulting number. So, but when we're initializing the list, we need to know like how many digits, how many entries are we going to need? And you could just if you just like work through a few examples, you can sort of convince yourself that it just is n1 plus n2 digits. So you take the number of digits in num1 and the number of digits in num2, add them together, and that's the maximum number of digits you could possibly need. But I want to actually prove it. So just starting like going through this in like a very simple example. Let's suppose num1 is, and I'll just say n1 because I'll assume that this is in integer. So n1 is the integer 999 and n2 is the integer 99. Okay. We'll say ni has di digits. So d1 is 3 because 999 has 3 digits, n2 or d2 is 2. Okay. So then if we have n1 times n2, this is going to be, okay, so if it were 999 times 1,000, if it were 999 times 100, then it would just be 99900. But it's not. It's 999 times 99. So it's this, but with one fewer occurrence of 999. And so we need to subtract 999 from this. And so that's the same as subtracting 1,000 and adding 1. So we would take the 9 here down to an 8. This is subtracting 1,000. Then we will add 1 at the end. Okay, so this is the product. Okay, and how many digits does this have? It says 5 digits, and 5 is 3 plus 2. Okay, so this is a good indicator that we're going to need 5 digits. But let's actually like prove this. Okay, so n1 n1 times n2 is going to be strictly less than, so the largest possible value of n1 is 999. And I should say here that like at this point, okay, so this is the example, but what I'm writing below here, this is abstract. This is general. Here, n1 and n2 could be any integers. And they could have corresponding digit counts d1 and d2. Okay, so whatever n1 and n2 are, we see here like for n1, if n1 has 3 digits, then the largest possible value is 999. And if you were to add 1 to that, that would be 1,000, which is 10 to the power of 3, which is 10 to the power of d1. So n1 is going to be strictly less than 10 to the power of d1. And that makes sense because 10 to the power of d1 has d1 plus 1 digits, right? 10 to the power of 0 has 10 to the power of 0 has 1 digit, 10 to the power of 1 has 2 digits, 10 to the power of 2 has 3 digits, etc. So 10 to the power of d1 has d1 plus 1 digits. And in fact, it is the smallest integer that has d1 plus 1 digits. And so that's why n1, that's another reason why n1 has to be strictly less than 10 to the d1. Well, yeah. Yes, because 10 to the d1, yeah, exactly what I just said. Okay, so n1 is strictly less than 10 to the power of d1, and n2 is strictly less than 10 to the power of d2 by the same argument. So the product is less than this, which is equal to 10 to the power of d1 plus d2. And again, like the thing that I said previously, 10 to the power of d1 plus d2 is the smallest integer with d1 plus d2 plus 1 digits. That's just a generalization of the fact that 10 to the power of n is the smallest integer with n plus 1 digits. So if n1 times n2 is strictly less than the smallest integer with d1 plus d2 plus 1 digits, then n1 and n2 can have at most d1 plus d2 digits. Okay, so we know that we're not going to need more than d1 plus d2 digits. And so we could move forward with that. This is actually sufficient. We could stop here because one of the things that we're going to have to do is we might we're going to have to remove leading zeros because there could be a case where we multiply the two numbers together and we get and we don't fill out all of the digits. We could have leading zeros, and so we're going to need some code to remove leading zeros, but let's just prove that we can need D1 plus D2 digits. So we might need D1. So we do not need more than D1 plus D2 digits. We might, in fact, need D1 plus D2 digits. For example, if N1, let's just say N1 is 5 times 10 to the power of D1 minus 1, and N2 is 2 times 10 to the power of D2 minus 1. Okay, we do need to check something here because I'm using the values of D1 and D2, but I have defined them to be the number of digits of N1. So it's sort of a circular definition. So we need to make sure that this actually holds. That if we define N1 in this way, is D1 actually the number of digits of N1? And if we think about this, so 5 times 10 to the power of D1 minus 1, 10 to the power of D1 minus 1 has D1 digits. I'm just going to write this here. 10 to the power of n has n plus 1 digits, because we keep referring to this fact over and over. Did I do this right? 10 to the power of 1 has 2 digits. Yep. Okay, cool. Here, 5 times 10 to the power of D1 minus 1. 10 to the power of D1 minus 1 has D1 digits. And multiplying by 5 will not change the number of digits because it's just 5 followed by D1 minus 1 zeros. And similarly here, 2 times 10 to the D2 minus 1 is just 2 followed by D2 minus 1 zeros, and so it has D2 digits. And so D2 is indeed the number of digits of N2. Okay, but here, then N1 times N2, this is going to be 5 times 2, so it's going to be, let's just write it down here. N1, N2 is 5 times 10 to the D1 minus 1 times 2 times 10 to the D2 minus 1. And we combine the 5 and the 2 to get 10. And then the other 10 to exponents we will combine into D1 plus D2 minus 2, and then this is just 10 to the power of D1 plus D2 minus 1, which has D1 plus D2 digits because of this. Blah. However, like I said, we might not need D1 plus D2 digits. For example, yeah, what's the simplest possible thing? N1 is 10 to the D1 minus 1. Same argument as before. This has D1 digits. N2 equals 10 to the D2 minus 1. n1, n2. This is going to be 10 to the power of d1 plus d2 minus 2, which has d1 plus d2 minus 1 digits. So we might need to, so we might not need d1 plus d2 digits. We might need one fewer. And so because of this, we might need to remove a leading 0. And we will need to think about that at the end. But in any case, this is why we set the result to be a list of zeros and a list of n1 plus n2 copies of 0, because we will need at most n1 plus n2 digits. Okay, all right. Multiply digits and add to result. Okay, so we're going to loop through the indices, and the way that we're going to do this is so what we're doing here is we're taking the integers in digits 1 and digits 2. Hopefully me walking around and pacing is not going to alter the audio quality. But yeah, so digits 1 and digits 2, we're going to be multiplying the digits together and appending them to the result. But result is not in integer here. It is a list of strings. And so when we multiply two digits together, we could end up with a 1-digit number or a 2-digit number. And if we end up with a 2-digit number, we're going to have to, I guess in either case, regardless of whether we end up with a 1-digit or a 2-digit number, we might end up in a scenario where when we add it to the result, we might need to carry over. Because we might, if it's 2 digits, or if we're adding it to a place where there already are numbers that get added on, then we could end up with a 2-digit number. And so we could need to alter 2 entries of the list. And we might need to, do some carrying. But basically, the point here is that we need to work from the least significant digits to the most significant digits. And because these numbers are represented as strings, where the greatest significant digits are on the left, we need to work backwards. We need to work from the right to the left. So we're going to loop through digits 1 and digits 2, but we're going to loop through the indices in reverse. So we're going to go for I in range, and we want to, when we're looping through digits 1, which has length n1, we want to start at the final index, which is n1 minus 1, because the length always is 1 more than the index of the final entry. And we're going to be decreasing, and we want to go all the way down to the very first entry, which has index 0. But the range function does not include the final entry, and so we need to go all the way down to -1, because this will ensure that the values returned by this range function start at n1 minus 1 and end at 0, because it will go up to but not including that final value of -1, which is what you would get if you were to subtract 1 from 0. We do the same. Okay, we do the same thing for J, but this is for N2. Actually, I guess it doesn't really matter. I'm going to do this I2 and J2. No, I1 and I2. Okay. Okay, so first we're going to get the product of the 2 digits, and this is just going to be digits 1, I1 times digits 2, I2. this does sort of beg the question, could we have just, typically if you're using, there's a lot of times where you can simplify your code by using enumerate instead of range. It seems like the range function might be slightly faster in this case, but at the end of the day, it doesn't really matter that much. Let's just stick with this. Okay, so we have this product of the two entries. And we need to think of like where this is going to come up in the final result. Okay, so if we think of this example that we were looking at before where n1 was 999 and n2 is 99, then we know n1 times n2 is going to be a list or the result. The result is going to be a list with 5 entries because 5 is 3 plus 2. And if let's just look at the final entries here. So we have, we're looking at the, if we're multiplying the 9 here and the 9 here, that's a little annoying. Let's just say we're doing this, 987 times 65. Okay, so if we're multiplying 7 by 5, multiplying the least significant digits together, this could certainly alter the final index, but it could also possibly alter the index before it, because we might need to carry. Okay, so we want to figure out like which indices are we going to be affecting. So if we're looking at the digits 7 and 5, 7, the index corresponding with 7 is 2 because it's 0, 1, 2. And the index corresponding with 5 is going to be 1 because 0, 1. Okay. And so then which indices are going to be impacted potentially here? Well, it's certainly, the product of 7 and 5, it's certainly going to impact the 4th index, but it might impact the 3 as well if we end up having to carry at all, or if the product has 2 digits, or both. And so we're using these. And so this is indices. You have I1 plus I2. That's the first index because 2 plus 1 is 3. Then the other one is I1 plus I2 plus 1 because it's the next one after that. Okay. So index 1 and index 2 are going to be I1 plus I2 is going to be the first one. And the second one is going to be I1 plus I2 plus 1. Okay. And then what is the total going to be? The total that needs to, what value needs to go into index 1 and index 2? Well, basically, if we're looking here, we need to multiply these 2 digits together and then add that result to whatever is already in the result thing. So what we need to do, okay, so here's what we end up doing. We're going to certainly take the product, and then we might need to add anything that's already there. And what's already there could be if there's anything in index 2. So if there's anything in here already, we will need to add it in. Okay, now let me think for a little bit. Why are we not caring about what happens in the first index here? That has to be because it has to be that. Oh, of course, we will get to that. Okay, so now what we're going to do is we're actually going to update the values. The result of index 1, or index 2, because remember this is the rightmost index, so this is just going to be total mod 10. So what we're going to do is we're going to take the product of these two digits, add whatever's already in index 2, and just take the remainder. Because anything beyond the remainder is going to be carried over into index 1. And then the result in index 1, we're going to take whatever's already there and we're going to add whatever was carried over. And basically, total mod 10 is going, so total could have 1 or 2 digits. Total mod 10 is going to be the first digit, and total floor division 10 is going to be the second digit. And if total is a 1-digit number, then total floor division 10 is going to be 0. And you can prove that this is the case. The fact that total mod 10 just gives you the first digit, that's essentially by the definition of modular arithmetic. But then with the floor division 10, well, let's see here. If you think about it, if you have a 2-digit number that's between n times 10 and that, okay. I'll just write this out because it's quick enough. If we have a 2-digit number x, which is at least 10 times n, and not more than 10 times n plus 1, then x over 10 is going to be strictly between n and n plus 1. So if we do floor division, or if we take the floor of this, it's going to be equal to So floor division Wait, is this necessary? Yeah, and this will just be n, and this will just be n plus 1. So, and this is, by definition, x floor division 10. It's you divide by 10 and then take the floor of that. And so it is going to be an integer which is greater than or equal to the integer n, and strictly less than the integer n plus 1. So it has to be the case that x floor division 10 is equal to n, because n is the only integer that is both greater than or equal to n and strictly less than n plus 1. Okay, and so that's why this gives us the first digit here. Okay, the only other thing that I want to discuss is, so here basically we got the total, which was a 1 or 2-digit number, and for that second digit, for the more significant digit, we just took the index and added the second digit of the total. So you could ask why we didn't do the same thing for index 2, which corresponds with the lesser significant digit. And the reason that we didn't do it here is because we need to carry. If the product is 9 and, okay, yeah, let's say like if the product is 9 and there was already a 2 at index 2, then when we add that together we get 11, so we need to carry the 1. So we can just include the 1 here in the first digit, but then for the second, yeah, we need to carry that 1. So we needed to add that, we needed to add what was in index 2 already to the total before taking mod 10 and adding the result to index 1 so that we could carry over anything, so that we could increase the value being carried over in case that value being carried over did increase as a result of adding the value result index 2. Okay. But yeah, so anyways, once you do this entire procedure, we have taken the product and we have used it to, we have updated the result. And you basically just have to do this for all pairs of values. The only other thing worth thinking about is just making sure that these index ranges make sense. Yeah, so like we sort of abstracted this from this example where we were looking at the final digits, and so we know it's going to work at the very end. And just to verify at the beginning, the smallest possible values for I1 and I2 are 0, so the smallest possible value of index 1 is 0, so that's not going to be out of bounds or anything. Okay, so this gives us everything that we need, and the only other thing that we need to do is we need to process we need to skip leading zeros. And so we're going to figure out like what index are we going to need to start at. Because we might need to start at the first index of result, but result might start with a 0. So we might need to start at a later index. So we're going to say the starting index, and I'll rename this to start index, is 0. And then while we're basically going to increase this by, we're going to increase start index by 1 until we get to the starting value. And the way that we'll know we're at the starting value is that the result at the start is not equal to 0. So while it is 0, we increase it by 1, and then eventually we are going to get to a start index which is non-zero, at which point we will stop increasing by 1, and we will have the index, the value stored here will be the index of the first non-zero entry of result. Okay, now the one other thing that I saw, let's see here, I did get, I think I used Claude to help with some of this coding and like coming up with solutions. And one of the recommendations that I saw was while this is true and start is less than length of result. And what does this do? This makes sure that our while loop terminates, because if we get to the end of result, basically we can't, wait, does this need to be in the reverse order? Because start index, in order to evaluate this, start index can be at most the length of result minus 1. So I think this actually needs to come first so that we can halt here if this condition is hit. But the other thing to think about is that this isn't actually necessary, because we already if we do get all the way through the list result and it's all zeros, then that must mean that either num1 was 0 or num2 was 0. And we already took care of that scenario at the beginning. So therefore, there has to be some non-zero value in result. And so this can never actually be triggered because we'll never be in this scenario. However, it is probably good to have this in because, you know, as you're programming, like you're going to make mistakes and there might be a bug, and like while loops like are like there's always a risk that you make a bug that results in a while loop repeating continuously and getting an infinite loop. And so it's nice to build something in here that will just be an extra safeguard to make sure that this while loop is going to terminate. But I tested this solution out without this, and it's not necessary. We've already proven that it's not necessary. And furthermore, when we looked at here, we said that we will need at most D1 plus D2 digits, but we also said like the minimum scenario, like the smallest number of digits that we could possibly need is actually D1 plus D2 minus 1, based on this. And so we might actually, so that implies that we're only going to possibly need to increase the start index by 1. Actually, I am very curious about this. I'm actually going to try this out. So we're going to have if result 0. Here. We're going to put the start index is 0, and if result start index is 0, then start index will be 1 instead. Because if it doesn't have D1 plus D2 digits, then it has to have D1 plus D2 minus 1 digits. And so if there is, if it doesn't use all of the digits, then it must use all but one of them. And that but one has to occur at the very beginning of the list because the list starts with the most significant digits. Okay, so I'm going to try this out and we will see if this crashes. Okay, but anyways, then we return the string. But the result isn't a string, it's a list. Okay, so it is a list, and it is a list of integers actually. So what we want to do is we don't want to return so we want to take the list of integers, we want to convert the integers to strings, and then we want to combine that, we want to concatenate all those strings together into a single string. Okay, so let's do that one step at a time. The first thing that we want to do is we want to create string digit for digit in result, but we need to start at the start. Okay. So this will create a list. This will create a list. This will create a list, which is all of the values of result without the leading 0 converted to strings instead of integers. Another way to write this is we could use the map function. Like so. And so this will basically take all of the values of result starting at start index and apply the function string to them and return the resulting list, which is exactly what we did before. Okay, so now we have a list of all of the digits that we need as strings, and we need to concatenate them together. So we will join them together. So this will take all the values in the string, or all the values in the list, put blanks between them, so like put empty strings between them, which is basically just putting nothing between them, and adding them, or concatenating them all together. Okay, so let's just check that this works. I am curious about this thing. Okay, it did not work. Integers are slices, not tuples. Did I need to be better about naming variables. Oh, there we go. I think I would. Is that MATLAB syntax I was using? Possibly. I don't know. But anyways. Okay, so this actually works. So that's interesting. So we do need to only skip at most 1, 0. And so this is all we need here. And then, yeah, this is our solution. In my looking around, this is like the most efficient, or this is, you can't, I haven't found ways to push the performance of this much further in Python. And so looking at this, how there's like a long tail here and there's like a bunch of solutions that use like almost no, that run almost instantly. I think this is just a matter of like programming languages. Just because like some of these other programming languages can be like inherently faster than Python. Python is known to be a slower language. It's very versatile, but it is, you pay for that to some extent with performance. And so I think this solution is fine. It's just we could perform better if we use a different language. But yeah, this is a perfectly acceptable solution. This is a bit of a nicer solution than the first one we came up with. It involved a little bit more thinking and a little bit more like math, I suppose. And yeah, so that wraps up this exercise.